take a moment and come up with the most general word you can think of. On the next chance you get, plug that word into a Google search engine, and if you're lucky, you'll get over 1 billion results in less than a second. Now think about what it's like to process over 1 billion things every second. It's absolutely enormous. So how does the Google search engine pull it off? Well, the answer lies in something known as Moore's Law. And it's actually more of a prediction which was made by Gordon Moore, the president of IBM, in 1965. Moore predicted that the number of transistors that we could fit on a computer chip would double once every 2 years. Now, for those of you who don't know, the transistor, in a nutshell, are those tiny components in your computer which register either a 1 or a 0. And since that's the only way computers know how to talk, it makes these transistors pretty important devices. Well, thanks to the drive of the semiconductor industry and thousands of scientists across the world, Moore's Law has become a reality, even to this day. And it's because of that that we have supercomputing search engines and devices such as this. This is actually a computer processor, and every one of your computers has one. It's essentially the brain of your computer. But the most amazing thing about this device is that it contains over 1 billion transistors within it, and it can process several billion commands every second, all in that little finger-held device. But despite all these great things I just told you, it turns out that all this growth and efficiency in computer speed that we've always taken for granted and assumed to be constant is going to come to an end in the next decade unless we do something about it, and this could pose a serious problem for society. I'm an electrical engineering student at the Pennsylvania State University, and recently I was given a chance to work with some of the leading scientists and researchers at the National Institute of Standards and Technology. There I got to see some of the research that goes into the computers, but also some of the concerns that these researchers have. And one of these is the so-called end of Moore's Law, or this kind of computing slowdown that we're facing. Now, these researchers agree that the clear reason why this slowdown is occurring is because of the fundamental limits of silicon, which is what we construct our current electronics out of. We've made our computer systems so efficient and so small that we're finally hitting a wall. Now, you might be wondering at this point, why is it a problem if my computer can't do over 1 billion computations every second? It's already amazing. Well, if you think about it, all of us are in the technical field. And at some point in your professional career, you're going to have a need for complex simulations or computations. Take, for example, arguably the biggest science project ever, the Large Hadron Collider. It turns out that in a year of data acquisition, the Large Hadron Collider will collect enough data that if you burn this data onto a CD or CDs, you'll have a pile of CDs 20 kilometers high. Not only is this an enormous amount of data, it's going to take a long time to process through it, and you want fast results in our field. And of course, with our population growth the way it is, if computing speed doesn't keep up, things in life are going to become slow and clumsy. So hopefully today I can show you a bit of the details of this computing crisis we have, as well as one potential solution that could revolutionize the way electronics work. So I told you a little earlier about Moore's Law, but here's an actual graph of what Moore's Law actually looks like, courtesy of the 2006 SPIE Microlithography Journal, and it shows the number of transistors versus time, with a diagonal line representing Moore's Law. Now, as you can see from the experimentally plotted data, we're actually beating Moore's Law. We're more than doubling the number of transistors that we can fit on a chip every 2 years. Not only is this amazing that we can put billions of transistors on a device, but transistors have become so efficient and small that for just a penny, you can buy 1 million transistors, which, if you ask me, is a pretty good deal. But despite how great this sounds, if you actually graph computing speed versus technology or time, you get a completely different story. And this graph is courtesy of the Electronics and Electrical Engineering Lab from NIST. And as you can see here, despite the fact that we've beaten Moore's Law, our computing speed is leveling off here at around 4 gigahertz, or about 4 billion computations per second. And this again is because of the fundamental limits of silicon. Because our transistors have been becoming smaller, they also become less efficient, and as such, they dissipate more heat. So much, in fact, that if we add any more transistors to our chip, the chip would melt. And if you want your computers to work, that's not exactly a good thing. Now, but even if we could get around this melting problem somehow, it turns out that our transistors are actually not going to get much smaller. Shown here is an Intel 45 nanometer transistor. Now, to give you an example of how small this actually is, we can fit 30,000 of these on the head of a pin. So small is it that this transistor shown here is actually 200 atoms in one dimension, which is incredibly small, but it's not going to get much smaller because we're going to hit the limit of an atom. And this, again, puts another cap on our computing capacity. So you might be wondering, how can we combat a problem like this? Well, you have to begin in the fundamentals, or in this case, the transistor. Now, if you look at the image I showed you earlier of the transistor, you'll notice it's kind of funny for two reasons. First off, it's completely in gray, and that's because you're looking at it from a special microscope that allows us to magnify things from the atomic scale. The other reason it's funny is because it's kind of granulated, as if it's pixelated and I did a bad job photo editing. Well, in fact, I didn't touch this photo at all, and those grains are actually supposed to be there. Each individual grain you're looking at is actually an atom. You are actually looking at atoms whenever you look at this device, and it shows how far our technology has gone. So at this point, you have to be thinking, whoa, back up. How can we even tackle this problem if we're already literally down to the atomic scale? Well, there are multiple paths you can take, and one of them is by replacing silicon with another substance that could be more efficient, because clearly silicon is limiting us. Another option is to continue pushing our transistors smaller and smaller until we reach the atomic limit. Well, in fact, one possible solution does both, and I'm going to show it to you right here. This picture here, you might be thinking I'm completely crazy, because it's just pink and a scale bar. But if you look a little closer, you'll notice there's something interesting about the center of the screen, and I'll help you out here. And I'll outline it here for you too, and you'll notice it's a little darker tint than the rest of the background. And that's because what you're looking at there, and there is something there, I'm not lying to you, is actually a single atom-thick sheet of carbon, and it is an atom thick. And it's also known as graphene. Graphene was discovered in 2004 by Andrew Geim from the University of Manchester, and it's heralded as one of the biggest scientific discoveries of our decade because of some of its incredible physical and electrical properties. Some of them might actually allow us to replace silicon with graphene in our electronics. You might have actually run into graphene before. If you roll it into a ball, you have your fullerenes, or your buckyballs. If you roll it into a tube, you get your carbon nanotubes, and there was a huge craze about that earlier. And if you stack it on top of each other, you get graphite, or pencil lead. And that's where graphene actually gets its name from, a single sheet of graphite. But the real reason why graphene is so incredible is because of its properties, one of which is that graphene actually conducts electricity. And it's kind of counterintuitive to think that something an atom thick would actually conduct electricity, but in fact graphene does it extremely well. Now, mobility is essentially a measurement of how fast electrons move in a certain substance, and that correlates to how fast devices can operate. Now, silicon has a typical mobility of about 2,000 mobility units, whereas graphene has a typical mobility of up to 25,000 mobility units, and this is about a 10-time increase. In fact, researchers have discovered that exceptionally pure samples of graphene can have mobilities that are 100 times better than silicon. Imagine our electronics 100 times faster than they already are. We clearly wouldn't be limited. Now, I mentioned earlier that silicon devices are actually pretty inefficient now, and they dissipate a lot of heat. Well, it turns out that graphene devices are highly efficient, and the key here is the smaller they get, the more efficient they get. In fact, Dr. Kostya Novosela from the University of Manchester and his research group have actually constructed actual graphene transistors. And they've published their work in the Nature article, The Rise of Graphene, and I show you a graph right here. From the graph, you can see transistor action. You can see a clearly defined high state, which could represent a 0 or a 1, and a clearly defined low state, which could represent the opposite. In fact, Dr. Novosela, who's one of the leading researchers of graphene, claims that silicon will be replaced by graphene. And with the way the research effort is going, the fact that we can actually construct graphene transistors, that they're highly efficient and small, makes this quote actually, a lot of people are beginning to agree with him. Now, of course, the obvious advantage of graphene is that it's tiny. It's an atom thick, which is as close to 2 dimensions as you're going to get. In fact, silicon transistors are predicted to break down at about 10 to 20 nanometers, whereas a graphene transistor has already been constructed at 1 nanometer and it's operational. Now, if you remember earlier, I showed you a 45 nanometer transistor. Well, this graphene transistor is 45 times smaller. In fact, so small that it's literally 10 atoms by 1 atom. In the 4 years that graphene's been discovered, we've already made graphene transistors that push us to the atomic limit of 1 atom, which is absolutely incredible. But you might think that 1 atom is weak. How can we construct something that's literally 1 atom thick? It might just break pretty easily. Well, that's exactly what researchers from the University of Columbia thought. And they actually performed a stress test on graphene, which is actually the bottom image here I'm showing. And that's a diamond needle tip, because anything else would break, actually. And what they found was that graphene is actually 100 times stronger than the strongest steel on the market. Not only that, but if you have a bowl-sized flake of graphene, and you put the weight of an elephant onto a pencil, and you put this pencil down on the graphene flake, the graphene wouldn't break. Now, of course, it's impossible to find a flake that large, but it goes again to show you how strong graphene truly is, and that, yes, we can actually use it in our electronics. So hopefully today you've become a little more familiar with the problem of this computing crisis that we're facing, because it's one that could dramatically affect our lives in the future. Graphene offers us a viable solution to replace silicon because of its incredible physical and electrical properties. Now, it might not be 10, 20, or even 30 years down the road before you see graphene on the market, and by that time, Moore's law may no longer be a law. But regardless, know that a revolution in electronics is about to come. It needs to come, whether it's graphene or not. But with the way the research is going, it might not be too surprising to find in the near future your computer constructed out of something as simple as pencil lead. Thank you.